So when you're dealing with the equilibrium constant, typically when you write it, you write KEQ. Okay, but sometimes what they do to try to make it help you understand it a little bit better is instead of writing KEQ, sometimes they'll write KC. And what that C stands for is it stands for the concentration. And we know that we measure the concentration in molarity. So all of the ones that we've done so far have all been, actually, without actually really saying it, all of the ones that we've done so far have all been KC. Notice that we have used all the examples we did, all your homework problems, all dealt with concentration. So KC is just another way of saying KEQ, but what it's doing is it's telling you specifically, hey, we want you to write it in terms of the concentration of that substance. And the reason that we use KC is because you can see right here, sometimes they use what's called KP. And KP, if you notice, again, is the same thing. It's still products on the tops, reactants on the bottom, raised to the power. But notice that the P here doesn't stand obviously for concentration. It stands for pressure. It means that they want you to write the equilibrium constant in terms of pressures rather than concentrations. So notice that there's no square brackets. You can't use square brackets when you're doing KP because that represents concentration. Okay, square brackets here, but no square brackets here. Okay, and then also notice that there's a capital P of NH3, a P for N2, and a P for H2. So no square brackets, and you have to use the letter P. Other than that, it looks just like KC does. So KC is in terms of concentration. KP is in terms of pressures. So example 3 says, write the equilibrium constant expression in terms of KC and KP for example 2 above. So example 2 was this one from yesterday. Okay, so in terms of KC, it's going to look just like the one we wrote before. KC is going to equal the concentration of NO2 squared. And again, that's our product. And there's 2 of them, so it's got to be squared, over the concentration of N2O4. Okay, and then in terms of KP, KP is going to equal the pressure of NO2. Notice regular parentheses, not squared, over the pressure of N2O4. And notice on the bottom one, I didn't put parentheses. You don't need the parentheses. Okay, if you let me show you another one here in just a second. Okay. But you don't have to use the parentheses. On this one, yes, you have to use the square brackets, but on KP, parentheses are not necessarily required. Okay, example 4, notice that on example 4, it doesn't say in terms of KC or KP. But if you think about it, KP, the pressure, can only be used when you're dealing with gases. Okay, if they're not gases, and it's an aqueous solution, then it has to be KC. So notice on example 4 when it says write the equilibrium constant expression for the reaction, but it doesn't say do it as KC or do it as KP. It just says write it. Okay, so you look at this and go, okay, that's a solid. So first of all, that's going to be out. But then Pb2 plus aqueous and aqueous, I have to write that in terms of KC. So that's going to be the concentration of Pb2 plus times the concentration of Cl minus, and that's going to be squared. Okay, so Kc is in terms of concentration, Kp is the same thing, just in terms of pressures. Now, once you know the equilibrium constant expression, now we can actually put some numbers into the equation, and we can solve for it. So based on that example from before, where we had Kc is equal to the concentration of NO2 squared, over the concentration of N2O4, well, now let's actually put some numbers in there. What is the concentration of NO2? Concentration of NO2 is 0.526. So we're going to go 0.526, we're going to square it, and then we're going to put that over the concentration of N2O4, which is 0.0429. So now I just go to my calculator, and I go 0.526 divided by 0.526, squared, almost missed that there, divided by 0.0429 equals 6.45. And we're going to talk about what that number means in just a second. Okay. Using example 1. So in example 1, and they want it in terms of Kp. So example 1, let's go back up to that here real quickly. Example 1 was the one with NH3 as the product. So that's going to be the pressure of NH3 squared over the pressure of N2 times the pressure of H2 cubed. So again, now we just put the numbers into the equation. So the pressure of NH3 is 0.441 squared over the pressure of nitrogen, so 0.166, times the hydrogen, 0.684, and that one does have to be cubed. Okay, so put this in your calculator as well. Make sure that you're getting the same answer as I am. So 0.441 squared divided by 0.166 divided by 0.684 cubed equals 3.66. Okay? And that is the equilibrium constant for that reaction. Now, last thing here real quickly. What does the equilibrium constant mean? What is the actual value? What does the number mean? It tells you, all that it does is it tells you about the equilibrium system. If the equilibrium constant is greater than 1, what we say is we say that the equilibrium lies to the right, and the right-hand side of the equation are the products. So basically all that it means is you have more products than you do reactants. Remember, equilibrium doesn't mean you have the same amount of reactants and products. It means that the rate of the forward and the reverse reaction are the same. So if the equilibrium constant is greater than 1, I mean, think about that. If it's greater than 1, then that means the number on the top is bigger than the number on the bottom. And the number on the top is the products, and the number on the bottom is the reactants. So it just means that you have more products than you do reactants. And then if the equilibrium constant is less than 1, so you don't have negative equilibrium constants, you don't have equilibrium constants of 0, it's really just, is it greater than 1 or is it less than 1? If it's less than 1, then that means you have, again, we say that the equilibrium lies to the left, and that means that you have mostly reactants in your reaction mixture. Okay, and that's really all that that value tells you. It tells you whether you have more products or whether you have more reactants.